Git Principles, Part 2, Fundamentals. Git is a tool that will track every file and every subdirectory of a particular project. Git is agnostic to the type of project or folder you are tracking. Your folder might contain application source code, the photos of an album, the pages of a book, etc. Git does not care. At the end of the day, when viewed as raw data, your project, regardless of how you may feel, is just a collection of files and subfolders. Git will track every edit that is made to every file and every subfolder that is added or removed from a project. Every time an edit is made, Git will track what was changed, who made the change, when the change was made, and why the change was made. Git does this via a local database that stores all the snapshots of your project at different points in time. This local database is stored in the .git folder at the root of your project. I have created a demo project called Tracks that holds a songs.txt file in it with my 3 favorite songs. Last by Burna Boy, What by Samwell, and Bohemian Rhapsody by Queen. Assuming we have Git installed, this is the Git command we would issue to start tracking the way this list changes over time. Now that we have issued the git init command, we can see that Git has added a .git folder to the root of our project. The hooks folder is where we can specify custom scripts that will be triggered by Git on our behalf at different points. The info folder is where some high-level metadata regarding our project will be stored. The objects folder is where all the snapshots of our project will be stored. This is the database I was referring to. The refs folder is where we can put human-readable names of the different snapshots of our project. The config file can hold some configuration that will change the way Git interacts with our project. The description file is where we can put a human-readable description of what our project is about. And finally, the head file is where we specify the active snapshot we are looking at of our project. Now that we've had an overview of the .git folder, let's take a closer look at the objects folder, or the objects database. Inside of it, we should see 2 folders that are both empty. The reason why they are both empty is because we have not yet taken a snapshot of our project. The following commands I will now write may seem bizarre, but all they are doing is taking a snapshot of our project. Now that we've taken our first snapshot, we should see some more folders inside of our objects database, particularly folders that are named with 2 characters and that hold files that are named with a random series of 38 characters. These files are where the snapshot we have just created has been stored. In the next demo, we will take a closer look at these files or objects that we see in our database. What I'm about to show you was taken from a book written by Scott Chacon and Ben Straub titled Pro Git. Let's start by introducing ourselves to 2 commands that will be very useful for inspecting objects in the database. The first command is this one, git catfile-p, followed by the hash of the object we are inspecting. The second command is this one, git catfile-t, followed by the hash of the object we are inspecting. Let's inspect the first object we see, this one. We can get the hash of this object by copying the object file name and prepending it with the 2 letters of the folder in which it is stored. Right? Now that we have these commands, let's run them and observe the output. We can see by the output that this is an example of a commit object. A commit object is a fancy name for a snapshot of our project. A commit object contains a reference to a tree object that we will see later. A field for tracking the author of this commit, as well as when they made these changes. A field for tracking who recorded or committed this commit, as well as when they committed it. And finally, a field where a description can be inputted or recorded that contains why this commit was made. Let's now run these cat file commands against the remaining objects in our database and observe the output. Here we can see the output of inspecting the first object. Here we can see the output of inspecting the second object. And finally, here we can see the output of inspecting the third object. This tree object is the object that is referred to by the commit. A tree object is how we specify the files and folders that exist at a particular depth of our project snapshot. The file contents are represented by blob objects. These three object types, blobs, trees, and commits, can be used to rebuild our project state at any point in time. If our project or folder were to contain more files or more subfolders, then these three object types would still be able to be used to rebuild our project state at any point in time. Most of the objects you will see in a Git database will be either blobs, trees, or commits. But there is one other type of object you will see in a Git database, and this fourth and final object type is the tag object. To be exhaustive, let's quickly create a tag object to make sure that we understand the concept of tags. Tags are human-friendly names for snapshots or commits of our application. The tag we just made gives us a human-friendly way of referencing the state of our application at a particular point in time. Let's say, hypothetically, that every month for the next 10 years, I were to update this list of my top 3 favorite songs. 10 years from now, I would be able to use the tags that I left along the way to easily pull up what my list looked like at different points in time. We could always use the randomly generated commit IDs to reference our state, but using a tag with a human-friendly name is much more intuitive than a random series of 40 characters. So now that we've seen examples of all the object types stored in a Git database, let's summarize our findings. Git stores all the snapshots of our project in a local database. This database stores all snapshots via 4 object types: blobs, trees, commits, and tags. Blobs are how file contents are stored. Trees are how folders are stored. Commits are how snapshots are stored. Commits are comprised of blobs and trees. And tags are human-friendly names for snapshots, aka commits. These 4 object types can be combined to rebuild the state of any project at any point in time. Coming up next is the third and final demo of this video, where we learn how the 38-character object file names are generated and why their contents are so cryptic. In short, the random 38-character object file name comes from the hash value of the object's data. If you are unfamiliar with the concept of hashing, here is a quick rundown of what hashing or a hash function is all about. A hash function is a list of instructions performed on an arbitrary chunk of data that deterministically results in or outputs a unique value of a fixed length. The hash function used internally by Git to generate the object file names is called SHA-1. I found a standalone implementation of SHA-1 written by a developer called Samwell, and we can take a quick look at it to get a feel for how SHA-1 works. Here is the implementation. SHA-1 can be written in less than 120 lines of JavaScript code as evidenced by this example. Walking through this SHA-1 function line by line is out of the scope of this video, but let's call this function a few times to get a feel for how it works. If I call this SHA-1 function with an empty string, this is the hash value that I get outputted. Because hash functions are supposed to be deterministic, if I call it again, I should get the same exact hash value. Let me call it with my name. Let me call it again. I get the same hash value. So the way that Git uses SHA-1 is for identifying identical files between snapshots that we take. All of the files that are the same as existing files will get hashed to the same object that's stored in the database. That is how the memory footprint of Git is kept so low. Now let's look into why the contents of the objects in our database look so cryptic. The reason why is that object data is not stored in raw format, but is stored in compressed format. The library that Git uses for doing file compression is called zlib. Let's now take a look at an example that combines the use of SHA-1 and zlib to rebuild one of the objects that is already in our database. Here is the example where we will recreate one of the objects in our database. The type of object we will recreate is a blob object. The broad strokes of this process are the same as the other object types, trees, commits, and tags, but the blob object is simplest, so we'll go with that. The first step of this process involves generating a header for the object type we are storing. Because we are generating a blob object, the header looks like so: blob plus a spacebar plus the amount of bytes needed to store the content of the blob. We will prepend the header onto the content and generate a SHA-1 hash. The SHA-1 hash is what will give us the name of our file. As far as the garbled contents that we usually see when looking inside of an object, we generate those via the zlib library. We will use zlib to compress the contents, and that will give us our final object. Let's run this and see what we see. Here we see that the first two characters of the SHA-1 hash are the same as this object. The remaining 38 characters are the same object file name that we see here. As far as these file contents, these are the same file contents that have been spit out by the zlib library. So hopefully that gives a feel for what you're looking at when you look at your object database. When you look in real-world Git projects, you will begin to see less and less objects and more of these things called pack files. Pack files are ways of storing your objects in an even more condensed format. Git already uses hashes, it already uses compression, but it goes a step further and indexes your object content into these things called pack files. This is the command that we can trigger to have Git create pack files on demand. You can see that we no longer have any objects, but we have pack files. Our pack files contain the same information that our objects were storing. Let me show you how to undo the pack process. For some reason, we have to move the pack file outside of the .git folder for this to work. Pipe the pack file content into the unpack objects command, and look what happens. We now get our objects back, right? So the pack process is reversible. Pack files hold the same data that objects store, just in a more condensed format. And that's all, folks. I attempted to give you all of the Git fundamentals upon which all further advanced aspects of Git can be deduced.